That's a good question. I'm one of the many engineering experts at ON Semiconductor, and I have an answer for you. New electronic dimmers for commercial and residential applications are being designed for compatibility with LED light bulbs. But there are many older dimmers already installed in houses, and these were designed to work with incandescent bulbs. These older dimmers come in two basic designs: a leading edge or forward phase cut control, or a trailing edge or reverse phase cut control. They perform the dimming function by blocking or cutting away part of the AC waveform. Since the incandescent bulb looks like a resistive load, the power delivered is proportional to the relative amount of the AC waveform allowed to pass. The majority of installed dimmers are of the leading edge, forward phase cut design and incorporate a triac to control the amount of power passed onto the bulb. The turn-on time on the triac is controlled by the manual dimming control button. The triac will then remain on until the AC signal crosses through zero, then it will turn off. It is this characteristic of the triac that causes the flickering of the LED bulbs. The maximum conduction time ranges from 120 degrees to 160 degrees of the 180-degree half-wave AC waveform, depending on the manufacturer. The majority of triacs used need a minimum of about 40 milliamps to function correctly. A 40-watt incandescent bulb has a resistance of about 360 ohms and draws about 333 milliamps RMS. When using a triac dimmer for this 40-watt bulb and setting it for maximum 180 degrees, the triac dimmer will turn on at about 20 degrees. At that point, the instantaneous voltage would be about 105 volts and would immediately draw about 290 milliamps. When the dimmer is turned down to about 1% on, or 2 degrees of the 180-degree AC waveform, the instantaneous voltage is about 34 volts and current is about 95 milliamps. This is still well above the 40 milliamps needed for the triac to operate correctly. An LED bulb draws significantly less current. In the circuit below, the bridge provides a semi-sine wave at 120 Hz with a peak voltage of 170 volts. The LEDs will not draw any significant current until the voltage out of the bridge is above the forward voltage of the LEDs, 100 volts plus the CCR regulation voltage, which is approximately 2 volts. The LEDs will draw current when the bridge voltage is greater than 102 volts. The CCR will then limit the current to 50 milliamps. The 50 milliamps is sufficient for the triac and the dimmer to turn on and operate correctly. But when the dimmer is moved below 20% on, the LEDs will stop drawing current and the triac will misfire and cause the LEDs to flicker. A simple solution is to add a load resistor across the output of the bridge. This resistor would need to be very large and capable of dissipating a lot of power, which is wasted power. For example, if your load resistor is 1 kiloohm, you will be dissipating greater than 15 watts. The resistor is only needed when the voltage out of the bridge is below that of the LEDs. By placing the resistor across the LEDs compared to across the bridge, the CCR can help limit the current through the resistor. The current being controlled by the CCR would be shared by the LEDs and the resistor. To improve this, the resistor is replaced with a 50 milliamp CCR. By adding a simple voltage detection circuit, the CCR in the circuit can perform both functions. Below 102 volts, CCR1 loads the triac, and above 102 volts, both CCRs control the current through the LEDs. The circuit below performs this function. This circuit was tested with multiple dimmers and operates the LEDs to give the same performance as incandescent bulbs do with no LED flicker. Thanks for your time. Keep those questions coming. We are here to help you solve your LED driver challenges. Have a great day.